Good morning.
Hi, Edward.
Hi, Edward. We're all happy for you to see me. And I just passed out the take-home quiz, which is due on Tuesday. And Edward, I'll post it for you online, although it's here, right there. There's the front of it. Take a screenshot. There's the back of it. Okay, now, we're going to start with a problem we skipped back on the T3, T4, T5 handout. So take out the handout that had tests 3, 4, and 5 on it and turn to problem 5. It says solve the given equation for x. And the equation is summation n equals 1 to infinity of sine x to the n minus 1 equals pi. So let's talk through this one together. This is an example of a problem that's on the AP test that requires no calculus. The only thing you have to actually know is that from pre-calculus, that the summation from n equals 1 to infinity of a times r to the n, I'm just going to actually pull up my dual user mode here. So some of you probably already know what the summation from n equals 1 to infinity of a times r to the n minus 1 is. There's a formula for it. What is the formula for the summation from n equals 1 to infinity of a times r to the n minus 1? It's a pre-calculus formula. Really, look at this. Isn't it an infinite geometric series? What's the formula for the sum of an infinite geometric series? Jessica, you want to give it a go? A over 1 minus r. First term over 1 minus the common ratio, and that's what we have going on here. What is the, notice the match between it's n equals 1 and n minus 1. So what is the first term of this infinite series whose value is pi? What is the value of a in this particular case? Well, to find out, put the first value of the index of summation in there. When n equals 1, what is the value of the term? Class?
1.
1. You can see it's an invisible 1 out front, so it's a over 1 minus r equals pi. Go ahead and solve this equation for x using a muck diagram. Muck, M-U-C, mini unit circle diagram. You may begin. Well, let's see how you're doing. Hopefully at some point along the line you wrote 1 minus sine x is a pith. Subtracting 1 from both sides gives me a pith minus 1. Multiplying both sides by negative 1 gives us 1 minus a pith. And getting the common denominator gives us sine x equals pi minus 1 all over pi. If you think about it, that number, about 3.14 minus, it's about 2.14 over 3.14. It's right around 2/3. It's right around 2/3. So if you're going to draw a muck diagram. That is a mini unit circle diagram in which you can visualize all the solutions. We draw on the muck diagram the y-axis from -1 to 1. 2/3 would be right around there. The number pi minus 1 over pi is right here. So x is all of the angles whose sine is pi minus 1 over pi. Now, one of those angles is in quadrant 1, but the muck diagram makes it clear that there are two angles. One's in quadrant 1, one's in quadrant 2. So x equals, can someone give me the value of x, which is really an angle, because you can think of it as an angle in radians from -infinity to infinity. What is the quadrant 1 value of x suggested by the muck diagram? Take a volunteer on this. All right, let's go with Scott.
X is equal to 0.
I want the exact answer, no approximations.
Okay.
What did you type into your calculator to get that 0 point, whatever it was you were about to say?
So that'd be the sine inverse of pi minus 1 over pi.
Pi minus 1 pi is correct. That's one of them. Raise your hand if you think you know the other answer. That's the quadrant 1 answer. Remember, the range of sine inverse is -pi/2 to pi/2, which includes quadrant 1. How can I use the answer that Scott gave me to construct the quadrant 2 version? By the way, here's a little visual hint. The angle that Scott gave me is like right around 2/3, 0.66, somewhere between 30 degrees and 45 degrees. It's an acute angle. So, by the way, had it been 31 degrees, then, yeah. Ethan, do you have it?
Just do pi over 2 plus.
Did you say pi over 2 plus?
Plus first.
Actually, no, it's not pi over 2 plus. You got to go, like, for example, if the angle Scott gave me had been 31 degrees, then the other angle, the quadrant 2 angle, would have been 180 degrees minus 31 degrees. So what is this angle? I'll bet you see it. Gwyneth, help me out here. What do you think the quadrant 2 angle is?
Pi minus inverse sine of pi minus 1.
Pi minus sine inverse of pi minus 1 over pi is right. Any questions on that one? By the way, back it up to the previous page. There is one more practice problem which will be super helpful for your take-home quiz due on Tuesday. There's one that we skipped up here, and it was up here in this region. My guess is you probably have some space in this region for note-taking right up here. Is it true that you have some blank space on the previous page right up here on problem 2?
Yeah.
Let's use that space to find the value of the summation from n equals 1 to infinity, changing to blue because I think that shows up a little better on the camera, from 1 to infinity of, and this is the problem I made up while you were doing the previous problem, 2 over n squared plus 4n plus 3. That's 2 over n squared plus 4n plus 3. If this problem were on the take-home quiz, how would you approach it? Well, here's what I would recommend you do. It's not just find whether it converges or diverges. I mean, nth term test gives no conclusion. And it would break down to a telescoping series, but the telescoping series test does not apply. Let's find out what the telescoping series is by using partial fraction decomposition. This is summation n equals 1 to infinity. Notice how the denominator factors into n plus 3 times n plus 1. So a partial fraction decomposition could be achieved using the cover-up method, something over n plus 3 plus something over n plus 1. Go ahead and perform the partial fraction decomposition in order to find out what's going on here. All right. Well, it appears when I use partial fraction decomposition that this is the series n equals 1 to infinity of, keep the minus in the middle. Alternating series work best when the minus is in the middle. It's 1 over n plus 1 minus 1 over n plus 3. Do you have any questions on how to perform the partial fraction decomp using the cover-up method? Now, friends, the fact that the denominators are 2 away from each other is a signal that, first of all, if they were 1 away from each other, then we'd be able to use the alternating series test. But since they're 2 away from each other, we're going to look for a pattern in the sequence of partial sums. I predict that everything's going to collapse down to 0, except for the first 2 terms, because the difference between the denominators is 2. So let's write out pairs of terms. I think when n equals 1, the first pair of terms is going to be a half minus a fourth. That's 1/2 minus 1/4. That's the n equals 1 pair. Write down the n equals 2 pair on your own. The pair of fractions produced by letting the value of the index of summation equal 2. So n equal 2. Right. Ethan, what's the second pair?
It's 1/3 minus 1/5.
Yeah, it keeps on going. Plus 1/4 minus 1/6 plus 1/5 minus 1/7 plus ... forever. Take a look at where things start to cancel. Switching to green, the telescoping effect occurs -1/4 plus 1/4. That's not green. Okay, so try it again to switch to green. So plus minus 1/5 plus 1/5. That's yellow. Minus 1/6 plus 1/6. They're all going away. Told you. They're all gone except for highlighted in green 2 terms. Everything else is going to go to 0. If we wrote out the kth partial sum, then the k's would be in the denominator. So when we take the limit and approaches infinity of a sub k, it would basically collapse to the first and these 2 terms. So the answer is 1/2 plus 1/3. The answer to this question, if something like this is on the take-home quiz, is simply 1/2 plus 1/3. Therefore, it's not an official test for convergence because the alternating series test does not apply. You would say, look, it converges to 1/3 or to 1/2 plus 1/3, 3/6 plus 2. It converges to 5/6. Therefore, the series converges. Any questions on that? Well, that finishes our little warm-up problems. And now, just want to give you a heads up, it's probably a good idea to get a head start on the problem set over the weekend also. Because even though you don't know how to do the whole problem set yet, there's a lot of them that you do know how to do. When it comes to absolute and conditional convergence, that we don't learn until next week. Yes, Jessica?
At the end of class, can you tell us which ones we can do?
Yeah, so the question is, at the end of class, can I tell you which ones you know how to do? Sure, we can. Let's take the last minute of class for that. Now what I'd like to do is switch over to any questions that you might have on the homework that's due today. Homework due today was assignment 8.3. We had the, basically it's P-series and the integral test. Any questions on the homework that was due today? I'd love to help you clear up any confusion you had. Jessica?
You didn't answer the last 3 questions.
Okay, so the question is, why did I not answer the last 3 questions? Take a look at that. Oh, wow, okay. Last 3, so determine the, just discussing these briefly, it looks like you would, yeah, interestingly, this one is nth term test right there, 85, nth term test diverges. And this one over here, you're gonna use the integral test because look, it's set up beautifully to do a u substitution with u equals natural log n, du is 1 over n dn. So this is a nice, how many of you used the integral test on this last one when you did it? That's good. And then on this one right here, 1 over 2n minus 1, what, yeah, review problem. What test did you use on this one? Notice the nth term test gives you no conclusion, it's not geometric, it's not a p-series. Did you do the integral test on this one also? Yeah, so you just integrate that. So, okay, thanks for the heads up. I'll have to go back and finish those, but it looks like in terms of selecting the correct approach, you knew what to do. Let's hit any other questions, concept questions that you have on the homework that was due today. All right, so we're learning 2 more tests to determine whether or not a series converges or diverges today. And those tests are called the direct comparison test and the limit comparison test. If you want, it's T6 and T7. Actually, I don't remember whether I put those online for people. Are T6 and T7 up there?
Yeah.
This is the lesson for 8.4, which is due on Tuesday. Please come and grab a copy of the paper notes if you want them. We're calling this the 8.4 handout. Watch your step, lots of cables going through the room. Okay, now we have first page of our lesson for the direct comparison and the limit comparison. Both of them are sufficiently sensitive to detect both divergence and convergence. Now, if we weren't pushed for time, we would go through, you know what? Actually, I think we can fit this in. See if you can remember what happened on the first 5 tests. Fill in the conditions for convergence, divergence, and the comments. Do rows 1 through 5. All right, let's see what we got here. So nth term test, you can check these in your notes, but remember, if the limit is 0, there's no conclusion. There's 2 ways to get divergence. Either the limit exists but is not equal to 0, or if that limit of the nth term does not exist, then the nth term test gives you divergence. Geometric series to categories are very easy to confuse with p-series. With geometric series, it's less than 1 converges, greater than or equal to 1 diverges. But with p-series, it's less than or equal to 1 diverges. And so I actually have those stuff because look, less than or equal to 1 is diverges, greater than 1 converges. And so yeah, those, believe me, these are easy to mess up. Although I guess the nice thing is that the equal to 1 is divergent in both. Pretty darn convenient. That's positive, decreasing, continuous for both. If the integral, the improper integral converges, you get convergent. If it diverges, you get divergent. Now let's learn the new ones, the 2 new tests, unless you have any questions on the first 5. There's 10 total. Let's hit 6 and, yeah, there's 10 total. Let's learn today direct comparison and limit comparison. In the direct comparison test, both of these have 2 steps. So direct comparison is, first step, 0 is less than or equal to a sub n, is less than or equal to b sub n, where b sub n is a function of n that you get to pick. you get to pull it out of thin air and bring it into the problem for direct comparison. And the second step is that series B sub n converges. So if you can sandwich A sub n between 0 and B sub n, and if B sub n converges, then clearly A sub n has to converge also. However, if you can pick some function B sub n such that 0 is less than or equal to B sub n is less than or equal to A sub n, and you can argue that series B sub n diverges, then look, A sub n is bigger than a divergent series, so A sub n would have to, by direct comparison, diverge also. So some of these sandwichings give you no conclusion. Like, for example, if you sandwich A sub n between 0 and B sub n, where B sub n diverges, then you don't know what happens to A sub n. It could be either converges or diverges. That would be no conclusion. Likewise, if you find out that A sub n is greater than a convergent B sub n, then that gives you no conclusion there also. You have to think about about whether or not you have sandwiched it so that you have a conclusion. By the way, since we're here, let's look at limit comparison. Instead of direct comparison, which is just with a greater than or less than sign, you can compare by taking a limit of a quotient. If you take the limit as n approaches infinity of A sub n compared to B sub n by division, compare them, and if you get a limit that exists that is greater than 0, can't be equal to 0, and if the function of n to which you're comparing A sub n is a convergent series, if series B sub n converges, then series A sub n also converges. However, step 1, if you're taking the limit as n approaches infinity of A sub n compared to B sub n by division, so you have to pick a B sub n out of thin air, take the limit of the comparison by division. If you get L greater than 0, and if the series that you pulled out of thin air happens to diverge, then A sub n also, series A sub n also diverges. So those are the two tests today. Let's do some examples of these so that you get comfortable with how these work out. So let's go to the next page. In preparation for the direct comparison test, you need some practice in finding out whether two functions compare with a greater than symbol or with a less than symbol. For example, and if you need to make this definitive, if you have to ignore a few terms at the beginning, if you have to ignore a finite number of terms to get it to work, that's fine. So, like for example, what's happening with the comparison between 1 over n and 1 over n plus 1? Is it less than, greater than, or equal? And this is for all n values greater than or equal to 1. So, 1/2, 1/3, like, come on. The thinking here, the logic is that bigger denominator means that the fraction is smaller overall, so 1 over n, would you agree, is greater than 1 over n plus 1 for all n greater than or equal to 1. So that's how the thinking goes. See if you can apply that thinking to the rest of the comparisons in this first row. Go ahead and compare greater than or less than. Now, kind of gets messed up with negative numbers here. So it's okay to say, look, we're going to ignore the numbers that, like, can't use 3, that would be division by 0. So let's say for all n greater than 3. So let's impose a restriction here, which entails ignoring a finite number of terms. And let's start our comparisons with n equals 4. Okay, so as long as we have n values greater than 4, then, okay, which is bigger? N is bigger than n minus 3, so bigger means, bigger denominator means smaller fraction. Over here, we're gonna restrict it to n values greater than or equal to 3, so we don't have to deal with negative numbers. Because, 3 squared minus 6 is positive, so we're in positive territory there. Which one is it gonna be here, class? Greater than or less than? Go ahead and call it out. I heard someone say less than. Keep in mind that this denominator is smaller. So smaller denominator means bigger number overall, so that's correct here. And then clearly this denominator is bigger than that when it's 10 bigger, which means it's going to be, the value of the fraction overall is going to be smaller. So go ahead and let's take a look at row 2. And in row 2, fill in greater than or less than for each comparison. So go ahead, fill them in. I'm going to tour the room, see what you come up with. A lot of you are already done with row 2. Your quartet of answers that I think you should have for row 2 are greater than, less than, greater than, and less than. Let's pause. Any questions on row 2? We're performing direct comparisons. This one, by the way, has a restriction. That's for all n greater than 25, and this is for all n greater than 2. Last row. Which one is bigger, n factorial or n squared? Well, it's like a horse race. Let's compare n factorial to n squared. When n equals 1, 1 factorial is 1, they're tied. So we can't say greater than or less than. When n is 2, n factorial is 2, n squared is 4. So the n squared horse breaks out into the lead. 3 factorial is 6, 3 squared is 9. N squared is still winning. 4 factorial is 24. Woo! 4 squared is only 16. So the n factorial horse breaks out in front, starting with n equals 4. So if n is greater than 3, then n factorial will be a bigger denominator than n squared. Bigger denominator means smaller overall, so we end up less than there, provided that's for all n, upside down it is for all n greater than 3. Likewise, we want to go, the horse race is done once it's determined and clearly visible once n is greater than 3 over here also. It turns out that n factorial, the n factorial horse, is faster than even the 2 to the n horse as long as n is greater than 3. N factorial diverges more quickly to infinity than 2 to the n does. This will also be less than. Over here we've got greater than and greater than, which there's something to be said for comparing those two. I mean, 5n squared minus 1,000, it starts out way down there. To find out when, you could use your calculator, but it's not until n is greater than 15 when you compare those two that the 5 actually compensates for the fact that it started out 1,000 behind. The 5 eventually does make up for that. So anyway, those are some comparisons that you're going to be using in the sorts of things you'll be using in the direct comparison test. So let's take a look at problem 1. This will be our first official example. And I wonder why it is we need to use the direct comparison test. I wonder if some of the other tests that we've learned so far would be just as good. I mean, nth term test clearly gives no conclusion. It's not geometric. You're learning how to just file through these in your mind. It's not going to be telescoping series, or at least not easily. No, it's not telescoping series, okay? I mean, it's not P series. Would you really want to integrate this? You use the integral test whenever the function of n is not too hard to integrate. And use substitutions would not work nicely here. This is not the easiest thing to integrate. You would not want to use the integral test here. This is why we have something called the direct comparison test. In direct comparison test, here's how we roll. We write direct comp. Underline means it's a test. You have to define a sub n, which is 1 over 3n squared plus 2. Make a circle problem, just like we've been doing a whole half page of circle problems where we compare, and pick a b sub n. The b sub n that you pick is going to be the simplest function of n that you can think of that has the same degree as the given one. So instead of 1 over 3n squared plus 2, just make it 1 over n squared. something that's simple to determine whether it's convergent or divergent. It's often a p-series or a, because we know what p-series do, it's often the harmonic series. So just compare it to this. That will be our pick it out of thin air B span function. So what's the comparison here? Would you put greater than or less than in the circle? Think about it and write down what you think goes in the circle. All right, I put a less than symbol in the circle because I think that the bigger denominator implies a smaller fraction overall. I think that a sub n is sandwiched between 0 and b sub n. I wonder if this is going to work. If b sub n diverges, then we have no conclusion. But if a sub n is trapped, sandwiched between 0 and a convergent series, then we'll be able to conclude that series a sub n converges. Let's think in advance here. What is b sub n? What type of p-series is it? Convergent or divergent? It is convergent. This is going to work. So those are the preliminary definitions for direct comparison. Let me shrink that down now a little bit. Here we go. 2 steps. Step 1 is delete, convert to blue. 0 is less than or equal to a sub n is less than or equal to b sub n. Check. What's the basis for checking that off? Well, look, I showed the analysis up here. Step 2. Series b sub n is a convergent p-series. Give a parenthetical justification of that. Nothing more. You don't have to run a whole p-series test. It's like a test within a test. Just say p equals 2, which is in the greater than 1 category. That's a parenthetical mini justification. It shows me that you remember your p-series categories. Therefore, series a sub n converges. That's our first example of direct comparison test. Does anyone have any questions on this proof that the series converges by direct comparison? All right, let's take a look at this one over here. E over pi. Interestingly, I don't think we need any fancy direct comparison. I mean, what test would you use? That's just a geometric series. Go ahead and run a geometric series test to discover whether or not this series converges or diverges. We can't forget the old tests. E pi's. Absolute value of E over pi is E over pi. 2.7 Andrew Jackson isosceles right triangle over 3.14, etc. Into what category would you place E pi's, class? Less than 1. Less than or equal to 1, that's a category for p-series. Less than 1 is kind of here. Therefore, series a sub n diverges. Let's go to the next page. Next page. So we got direct comparison. Those are a lot of fun. Solutions are posted. At least I think I finished the homework and the solutions are posted. Let's do an example. We did. Oh yes, Jessica.
Doesn't that one converge?
Yeah, did I say diverges? That's ridiculous. Thank you for catching that. If it's less than 1, it converges. Sorry, that word. Converges. Good call. Okay, let's go to the next page. Here's some more examples. By the way, interestingly, for direct comparison, let's just think of what the comparisons would be. I mean, clearly, let's just practice picking things out of thin air. We got a sub n equals 2 to the n over 3 to the n plus 5. What function would you be inclined to pick out of thin air to compare this to?
2 to the n over 3 to the n?
Okay, Jessica says 2 to the n over 3 to the n, which is 2/3 to the n, right? 2 to the n over 3 to the n, that will be our b sub n. And by the way, that's a good call because it's easy to compare them. This has a bigger denominator, so it's smaller overall. Oh, this is interesting. What is B sub n? It's not a P series. What type of series is B sub n? Geometric. Convergent or divergent geometric? Convergent. So this will work. This will give us a conclusion. How about this one over here? So instead of finishing the whole thing, let's just talk about this one in general. We've got A sub n equals E over n to the pi. To what would we compare that? We're exercising our ability to pick functions of n out of thin air that would be nice for comparison purposes. Now, pi is about 3 point, okay, pi, E, it's not a P series. It kind of looks like a P series, but it's not a P series. What's stopping it from being a P series? The E is stopping it. What do you think about comparing it to 1 over n to the pi? Would it compare, and sometimes you have to just find something, I'll give you a conclusion. Would this be greater than or less than, by the way? Yeah, it's got to be greater than. And so it's bigger than this. By the way, what is 1 over n to the pi? A convergent P series or a divergent P series? Yeah, it's convergent. So this is no conclusion because this thing is bigger than a convergent series. So we need to sandwich A sub n between 0 and a convergent series. So this one doesn't sandwich. It gives you it's bigger than convergent, which means logically it could either converge or diverge. So that wasn't the right one to pick out of thin air. I wonder if, though, does anyone see how we can make an adjustment, though? Because there's a lot of P series we could have picked. We happened to pick one that was smaller than this one. Do you think we could pick one that still converges, but that's bigger than that one? Max, what do you think? Do you have one in mind?
Just do like E+1.
E+1. So, but that's not a P series then. It's got to be a P series, so it's got to be 1 over n to the something.
Maybe like 1 over n to the pi plus 1.
Or just 1 over n to the 4th. Oh, just 1 over n to the 4th. That will probably make up for the fact, the fact that it's just a 1 up there, that's not too hard to deal with. In terms of 2 horses, this, because of the 1, or let's go n to the 4th, or n to the 5th. We've got a lot of series that converge. So I'm just gonna pick, you could even pick n to the 7th. Even though 1 is less than e, the fact that we've got an exponent of 7 down there, that's gonna overpower the fact that the numerator is smaller. So now this is huge. Now I think we're in business. Because, greater than, I flipped that one. So, so the fact that this is a greater means it's, if that one is less than, rats, we're still, okay, so we went the wrong way, didn't we? Went the wrong way on that one. This is what it's like to pick things out of thin air. It's like you do it by trial and error. So since 7 didn't work, what do you recommend I use? 2. Let's go n squared. Because now this is clearly bigger, so it's going to be smaller. Now we got it. Now it's sandwiched between 0 and a convergent P series. So that's the kind of thinking you use. And then just in terms of what would I pick for this last one, 1 over the square root of n squared minus 1. Notice the square root of n squared, the degree is basically 1. This is your classic situation where you're going to want to compare it to the harmonic series 1 over n. That's what my intuition tells me. Now, which one is bigger? Let's see. I think because of the n squared minus 1, let's take 10. 10 squared minus 1, that's square root of 99, which is a little bit less than 10. This is 10, so this is a bigger denominator. So it's this denominator is bigger than that one, so it's going to be smaller overall. So now, look at what we've done to a sub n. We've shown that it's bigger than 1 sub n, which is a divergent. It's bigger than a divergent, which is going to show by direct comparison that this is going to diverge. Series A sub n will diverge. So you have to be creative with direct comparisons, that you have to pick things that work. Now, let's go down, make sure we get an example of limit comparison in here. So limit comparison, let's do number 3. In number 3, let's write limit comparison, and we're going to pick an a sub n equals n over, it's given, n plus 1 times 2 to the n minus 1. We have to pick a b sub n that basically has the same structure but is as simple as possible, same degree. Look, the n's are, it's degree 1 over degree 1. This is basically a 1 over 2 to the n minus 1 would be the simplest similar function. Now, look at what happens when I go through the 2 steps. I'm gonna skip this problem and just make sure you get one good example. Here's step 1. Take the limit as n approaches infinity of a sub n over b sub n, which in this case is the limit as n approaches infinity of n over n plus 1 times 2 to the n minus 1 over 1 over 2 to the n minus 1. Notice how when you flip the denominator fraction up top, the 2 to the n minus 1s are going to cancel, and you just get degree 1 over degree 1 equals 1, which is in the greater than 0 category. That's all we needed. Step 2, series b sub n is, what is it? What can we say about 2 to the n minus 1? It's 1 over 2 times 2 to the n, or 2 to the negative 1 times 2 to the n. It's the same thing. So if you looked at the series, just briefly, I mean, it's basically 2 over 2 to the n. And pull the 2 out front, and it's 1 over 2 to the n. So it's really a geometric series with an absolute value of r less than 1. So we can say that it's a convergent geometric series. Convergent geoseries. And since b sub n, the function to which we compared it, converges, then we can say, therefore, series a sub n converges. There you have it. Have a great 3-day weekend. The take-home quiz is due on Tuesday, along with the homework. Yeah, so problem set, I'll tell you right now, I actually want you to wrestle with whether or not you know how to do them or not. But when it comes to the section on convergent, it's only the first section that you can possibly do. But when it comes to ones that have to do with absolute convergence and conditional convergence, you haven't learned that yet, so you can skip that section and everything after it. So it's only section 1 that you should attempt, but you won't know how to do all of them. The ones with factorials, Jessica, those are typically the ones that you need the ratio and root test for, which you haven't learned yet. Also, the alternating series, we don't know those also. So if you have -1 to the whatever, if you have an alternating series, you don't know those either. Thank you.
And then the quiz feedback.
You can hold on to the quiz. Yeah, you're welcome. We'll see you. Have a good weekend.